So y equals tan x. So when you graph tan, it looks like this. So one possible limit statement would be as x approaches pi over 2 from the left of tan x, you would say it is positive infinity. Tan x. How many limit statements would we have to write if we wanted to write all of them down? An infinite number. Okay, that's shortcut for finding vertical asymptotes. All you need to do is factor the numerator factor the denominator, and it's the term for the vertical asymptote. Vertical asymptote is the term in the denominator that doesn't cancel. Okay? So if you had something like this, factor the numerator, x plus 2, x plus 3, factor the denominator, x plus 2, x plus 4, which term in the denominator that doesn't cancel. So the vertical asymptote is going to be at x equals negative 4. Okay? That's all it is. Factor the top, factor the bottom. The one that doesn't cancel in the bottom is the vertical asymptote. If both don't factor, then there's two vertical asymptotes. If this happens, today's word, it's a hole. Okay? Flip the page. End behavior models. Oops. So in your graphing calculator, in y1 I want you to put f of x down, and in y2 I want you to put g of x down. Okay? And in your Windows setting, so there's f of x, there's g of x. Are they virtually identical when you look at them from far away? Yeah, they look the same. What I'm trying to get at here is when you move out towards the edge of the graphs, all of this information here, all of this part of the equation, while interesting, it isn't very powerful. When you take a number and raise it to the 4th power, that number is so large that it basically dominates everything else. Close to zero, these numbers are more powerful. But away from 0, the highest powered term is always the most powerful thing. And that's why it's called end behavior, because what we're doing is we're looking at the ends of the graph. That's what end behavior means. You're just wanting to know what's going on at the end, at both left-hand side and the right-hand side of the graph. That's all that end behavior is. So confirm analytically, well, that means, all that means for you to do is to show the limit as x approaches infinity of 3x to the 4. Well, maybe you can see what will happen. Minus 2x cubed minus plus 3x squared minus 5x plus 6. So we're going to take the function f of x and we're going to divide it by g of x. And we're going to see what happens. So if you look at the denominator, you can split you can split the denominator up over all of those functions. Well, when you do that, what happens to that? One whole. What about this one? Good. 2 over 3x. What about the next one? 1 over x squared. What about the next one? 5 over 3x cubed. And what about the last one? 2 over x to the 4th. Okay. So we've got all these little bits of leftover stuff. What's 3 times infinity? Infinity. 2 divided by infinity? 0. What's 1 over infinity squared? What's 5/3? What's infinity cubed times 3? Take that answer, 5 divided by that answer. 0. What's 2 over infinity to the 4th power? 0. What's 1 plus 0 plus 0 plus 0? 1. Well, what we've just said is the only, as you get out towards the end of the graph, the only part of the graph that matters is the it's just the highest powered term. Nothing else matters. It basically says that the graphs are identical out at the edges. Only out at the edges, not in the middle, busy part of the graph. Because if we looked at this graph over a much smaller window, they're not going to look the same. No. NB edges of the graph, middle of it. Okay. We have 2 kinds of end behavior models. The one is the right end behavior model. That's when we go to positive infinity. And then we have a left end behavior when we go It's negative infinity. Okay. So show that this is the FM behavior model for, okay. So in Y1, we're going to graph x plus e to the negative x, and in Y2 we're going to graph y equals x, and we're going to see what happens here. So there's x plus e to the x. There's y equals x. Is y equals x a right-hand behavior model or a left-hand behavior model? Right. Why? Right-hand behavior model. So there's x plus e to the negative x. There's e to the negative x. So the graph of y3 e to the negative x looks like this. Is e to the negative x a left-hand behavior model or a right-hand behavior model? Why? Well, a better answer would be, here's my thinking. And I'm going to look at, we're just going to look at y equals x plus e to the negative x. If I take a number like x, let x equal 3, which is more powerful? 3 or e to the negative 3? Maybe we need to think about what e to the negative 3 means. It means 1 over 2.7128182818 to the power of 3. Is that a big number or a small number? Small number. So which one's more powerful? The number 3 or 1 over e to the 3? 3. What if I change the 3 to a 15? (15) is still more powerful. So as x gets large, that e to the negative x gets really small, and so the only part that matters is the x part. Make sense how that's kind of going on there? Okay, now if we use negative 3, all you got to do is put a negative here. Well, what's a negative negative? Plus. Which is more powerful? The number 3 or e cubed? E cubed is going to be more powerful. Because when you cube a number, cube a number bigger than 1, it grows pretty fast. Right? If you look at negative 15, yeah, negative 15 is pretty big, Mr. App. But if you take e and you raise it to the power of 15, it's really big. Okay, so the left-hand behavior model matches the e to the negative x part because when you take a negative number and you multiply it by negative 1 and you raise it as an exponent, it takes control. Yeah? So you just got to think about your exponents. Flip the page. So the easy way to find the end behavior model is to find the highest powered term in the numerator and the denominator. So what's the highest powered term in the numerator? 2x to the fifth. What's the highest powered term in the denominator? And now simplify. Shouldn't be F, we should use some other letter. G. Simplify it. Two over 3 x cubed. So as we go out to infinity, or negative infinity, that function f of x will basically look like 2/3 x cubed. There won't be much difference between the two of them. They'll look the same. They're doing the same thing. Well, what's the end behavior model for the next one? Two x cubed over 5x cubed. Simplify that. 2 over 5. So as we go out into infinity, the graph will look like y equals 2/5. I think that's pretty cool. I don't know if you guys do, but I do. Okay, so how do we do this to find limits? Well, what's the end behavior model? Two x to the fifth divided by 3x squared, is it not? 2x to the fifth divided by 3x squared. Okay, simplify that. Over 3x cubed. Okay, what's infinity cubed? Infinity times 2/3? Still infinity. Okay, do the same thing for the right-hand side. Limit as x approaches negative infinity. Do you get the same answer? Careful. Okay, that matches. What's negative infinity cubed? Negative infinity times 2/3 is negative infinity. Okay, now what is this telling you? I don't know. What it's saying is as I go out to the right, as I go out to positive infinity, the graph climbs up and up and up and up and up. And as I go out to negative infinity, what happens to the graph? It gets smaller and smaller and smaller. So what we actually know is the graph's going to do some really funky things in the middle, but eventually it's got to go and drop off the table on the left-hand side. We know it has to do that. We have no idea what it's doing on in the middle business, but we know as we go out to the right, it's got to climb up, and as we go out to the left, it's got to fall off the table. Okay? Yeah, I know, nice sound effects. Okay. 2B, what's the end behavior model? What's the highest power on the top? Come on. What's the highest power in the top? 2x to the power of 3. What's the highest power in the bottom? Good. What happened? What happens to the x's? So what are you left with? 2/5. Okay, do the right-hand side. So what are you left with? 2/5. Okay. What does that tell you? No. What? No. They both end at the same height. Well, that's one way of saying it. As we go out to the right, or sorry, as we go out to the left, as we go to negative infinity, our y value is 2/5. And as we go out to positive infinity, our y value is 2/5. What do we call that? Well, it doesn't have to have line symmetry. There you go. ASY. MPTOTE. There's a horizontal asymptote at y equals 2/5. Okay, C. What's the end behavior function? Pardon me? 4x squared over 2x cubed. So, simplify that. 2 over x. What's 2 over infinity? What's 2 over infinity? 0. Okay. And the limit as x approaches negative infinity, you're going to get 2 over x again. What's 2 over negative infinity? 0. So if we were to graph this, we know as we go out to the right, the graph's got to get really close to the x-axis, and as we go out to the left, the graph has to get really close to the x-axis. So what do we know about? What do we know about this graph then? There's horizontal asymptotes. So which of the functions have horizontal asymptotes? B and C. Why? Because the limit as x approaches infinity, positive or negative infinity, of the function, what did it equal? Did it equal infinity, or did it equal some number? It equaled some number. Some number. Not infinity. Now how do I do this really quick? You thought that was fast. The limit as x approaches infinity of, I don't know. You know what? I'm not even going to do it that way. You know what degree means? The degree of this is x squared. That's right. Yeah. So if the degree of the denominator is bigger than or equal to the degree of the numerator, then there must be a horizontal asymptote. Exclamation point. Must. Shall. Okay? Okay? That's it for today, but I want to maybe do, so if we start with y equals 2x squared plus 5x plus 9 over 3x squared plus 6x minus 18. Is there a horizontal asymptote? Yes or no? Yes? Okay, Matt, how do you know? So what is it now? Can you tell me what it is? What's the highest power term on the top? So 2x squared. What's the highest power term on the bottom? 3x squared. What happens to the x squared? So you're left with 2/3. So that's what I want to see for work. Is there a horizontal asymptote? Yes, there is. And it's y equals 2/3. Okay? What about this one? Is there a horizontal asymptote? You might have to do one more line for this one. What is it? 2 over 3x. So what's 3 times infinity? Infinity. 2 divided by infinity. So is there a horizontal asymptote? Yes, there is. It's y equals 0. So if the power on the top equals the power on the bottom, then the horizontal asymptote is just the coefficient. If the power on the top is smaller than the power on the bottom, then the horizontal asymptote is 0. That's actually what I do all the time. But if I say, prove it to me, then you have to do this. If I ask you, is there one and what is it? Yeah, I just look at it and spit it out at me. But if I say, prove it to me, I need to see that circled part. Okay? Clear? It's not that bad. Okay. Where are we going with this? Eventually, I'm going to ask you to graph this without touching a calculator. And you'll be able to do that. Because you'll be able to talk about horizontal asymptotes. You'll be able to talk about vertical asymptotes. We're going to talk about holes. We're going to talk about maximums and minimums and how you can get out all of that without actually touching your graphing calculator. Okay? There you go. All done. Homework, you guys need to get a good bite into 2.1.